Everyone, welcome to the first lecture of Chapter 11. Chapter 11 is on liquids, solids, and intermolecular forces. So we're going to take those Lewis structures that we've gotten so good at drawing over the past couple chapters and then combine that with polarity that we were working on in the last chapter and molecular shape to see how the molecules interact with each other. So this is intermolecular forces. So these will be forces between molecules. So we've learned about intramolecular forces with our forces within a molecule. And actually, I've got this all laid out for you on the next slide. We have intramolecular forces, which are the bonding forces. We've covered those so far, and those are the forces within each molecule. And so these would be things like ionic bonding, covalent bonding, right? They influence the chemical properties of the substance. How does it react with other molecules? Today's topic will be on intermolecular forces, and these are not the bonding forces. These are forces that are between molecules. So how does one molecule of water interact with another molecule of water? And so these will be influencing the physical properties of the substance. Is it a solid or a liquid or a gas at room temperature? And things like that. Okay, so our intramolecular forces are very, very strong. So these are our ionic bonds and our covalent bonds. These are, like I said, intramolecular forces. Very, very, very strong. But as far as intermolecular forces, right, we have a couple different ones. The ones that we will be covering are these bottom three. Okay, these are intermolecular forces, so between molecules. This ion dipole one is as well. We're not going to talk about it too much in this class. This would be like if sodium comes into contact with something polar like water. Which is a very strong interaction. It's the strongest of our intermolecular forces, this ion dipole, but we're going to stick with hydrogen bonding, dipole-dipole, and London dispersion forces. So today we'll be looking at what are those and how do we recognize them. Okay, so our dispersion forces are going to be between any molecule in general. They are extremely weak intermolecular forces, and they're caused by what's called a temporary dipole, or temporary separation of charge. I'm going to spend quite a bit of time trying to explain dispersion forces to you in a little bit. We also have dipole-dipole interactions. These will be between polar molecules. Polar molecules will have dipole-dipole interactions. They will also have dispersion forces, but our dipole-dipole interactions usually are the more important force. When we have a nonpolar molecule, nonpolar molecules, all they can do is have dispersion forces. They can't form dipole-dipole interactions or hydrogen bonding or ion dipole. So if you have a nonpolar molecule, your only option will be dispersion forces. But like I said, polar molecules also have dispersion forces. There's just usually a more dominant type of force that's happening. So polar molecules will have dipole-dipole interactions, and then hydrogen bonding is a very strong intermolecular force. We're going to spend some time talking about that. Hydrogen bonding, and I want to make this really, really clear, hydrogen bonds are not bonds. They are not bonds. It is a very poor name for this type of interaction. It is an attraction. It is an intermolecular force between molecules, but it is not a bond. So I recognize it says hydrogen bonding. It is not a bond. And this is when molecules that contain a hydrogen that is specifically bonded to a fluorine, an oxygen, or nitrogen. So like hydrogen, like HF, or H2O, or NH3, but that hydrogen must be bonded to one of these really electronegative atoms. And I know you like my chemistry puns. So my one here is that hydrogen bonds, they just want to have fun. So there you go. And then ion dipole is the strongest of our intermolecular forces, and it's when we have something that's, an ion like sodium or chlorine, and it's attracted to a polar molecule. So an ion is attracted to something polar. So this is what we see when like sodium chloride dissolves in water, right? Each one of those, the sodium ion, that Na plus and that Cl minus, they get pulled off by the water and then surrounded. That's in our example, right? So like I said, NaCl in water, this would be our example of ion dipole interactions. But I think that's fairly straightforward. We're going to spend our time talking about the other three because it's a little bit more challenging to see those. So hydrogen bonding. Like I said, it is an attraction, not a bond. It's a really, really strong attraction, but it is not a bond. There's no bonds being formed. There's no electrons being shared, no electrons being transferred. It is an attraction between the partial negative on the nitrogen and the partial positive on this hydrogen or this hydrogen, right? It could also form here. Okay, it is an attraction, not a bond, between a hydrogen and a more electronegative neighboring atom, such as oxygen, nitrogen, or fluorine. Those are the only ones. So if you have like methane, right, CH4, methane cannot form hydrogen bonds because those hydrogens are not attached to a highly electronegative atom. We need to have the hydrogen, like here, the hydrogen is bonded to the oxygen, or these hydrogens are bonded to the nitrogen. So you have to have a hydrogen bonded to a really electronegative atom, like this. And then once, after you have one bonded to the really electronegative atom, then it can form this attraction to another really electronegative atom. That could be the same, or it could be, it could be different. So like it could be attracted to another water molecule. But it must be, this hydrogen here must be bonded to a really electronegative atom and attracted to a really electronegative atom in order to be considered a hydrogen bond. And like I said, remember, hydrogen bonds, they want to have FON. That's how you'll remember these. So here's some more example. These hydrogen bonds are occurring between polar molecules that contain hydrogen atom that is bonded to a really electronegative atom. And it's got to be fluorine, oxygen, or nitrogen. So like here, in this first example, we have two NH3s, right? And so here, the hydrogen is bonded to the nitrogen and attracted to the other nitrogen. So this first bond, that's a covalent bond, right? We have electrons that are being shared. That's not the hydrogen bond. The hydrogen bond is the attraction between this hydrogen and the nitrogen. Okay, so it's between two molecules. So this would be the hydrogen bonding in ammonia. Same thing over here for water, right? We have a hydrogen that is bonded to a really electronegative atom and then attracted to another really electronegative atom. So the attraction part is what is the hydrogen bond. Okay, and so we need to have, like I said, this partial positive hydrogen and partial negative nitrogen or oxygen or whatever the case may be. But make sure that you're not calling this actual bond here the hydrogen bond. It's the attraction between the really electropositive hydrogen and the really electronegative atom. The attraction between them is called the hydrogen bond, which again, not a bond, just an attraction. So here's another example. We have, a hydrogen that's bonded to a really electronegative atom and then attracted to another highly electronegative atom. So that's what we have to have. This is methanol, CH3OH. So we need to have, oxygen bonded to a really electronegative atom and attracted to another one. And the way that you'll recognize this, like if I had just written it out like this, you could draw the Lewis structure and then see that it's got a hydrogen bonded to the oxygen. But if you see from either the structure or the Lewis structure that they have an HF group, an OH group, or an NH group, or NH2 group, that works too. Then you can recognize, oh, hey, that's telling me that there are hydrogens bonded to those really electronegative atoms, right? Because we're looking for nitrogen, oxygen, and fluorine. So if you see one of those and they have a hydrogen, attached to it in the structure, in the molecular structure, in the, just the way you've written it out, then you'll recognize, oh, hey, that has hydrogen bonding. Since these have these interactions are really, really strong, this causes these molecules to have unusually high melting and boiling points. So like normally, when we have really, really small molecules, which we'll get to a little bit later, when we have really small molecules, the only thing, keeping them together is really these London dispersion forces. And a lot of times we can correlate an increase in molar mass with an increase in boiling point and an increase in melting point. So things that tend to be heavier tend to have higher melting points and higher boiling points. But molecules that have hydrogen bonding have unusually high melting and boiling points because these interactions, right, these hydrogen bonds are keeping them together. So if we think about water, water has a molar mass of 18.02. That is a really small molar mass. Water is a very, very small molecule. So most things we know about, melting and boiling points would lead us to believe that water would be a gas at room temperature. Like if we think about oxygen, right? Oxygen, O2, has a molar mass of 32 grams per mole. Oxygen is a gas at room temperature. Or carbon dioxide, 44.01 grams per mole. It's a gas at room temperature, right? And so something that has 18.02 grams per mole, like water, we would think, of course, it's even smaller than these. It should clearly be a gas at room temperature. But it's not. It's a liquid. And the reason that water is a liquid is it has this hydrogen bonding, right? Water is a really good example of hydrogen bonding. And those hydrogen bonds form those strong attractions between the water molecules and keep them in the liquid phase, whereas other molecules that don't have hydrogen bonding, like O2 or CO2, right? There's no hydrogen in either one of those. They don't have hydrogen bonding. They will actually only have London dispersion forces and are therefore gases at room temperature. So things that have hydrogen bonding will have unusually high melting and boiling points for their molar masses, which is really cool. So one of the reasons why there's life on Earth. Water can hydrogen bond. Again, this is an attraction, not a bond. But remember this, though. It has unusually high melting and boiling points. So here's some more example for you bio peeps. Hydrogen bonds are found all over DNA. So if we look at this NH2 group up here, and if we think about it, instead of being as NH2 written like that, you could think of it as being nitrogen and hydrogen and hydrogen. We've got a lone pair happening somewhere there. So this hydrogen is bonded to a really electronegative atom and attracted to a really electronegative atom. Same thing here. This hydrogen is bonded to a really electronegative atom and attracted to another really electronegative atom. Hydrogen bonding is what holds together the double helix in DNA. So super, super cool. Same thing here. We've got all of these right here. I'll pick this one in the middle because it's easy to see. Nitrogen is bonded, right? That hydrogen is bonded to a really electronegative atom and attracted to another really electronegative atom. Same thing for these other two, right? If we move one of those hydrogens down here, we'll just kind of add the lone pair, right? This hydrogen is bonded to a really electronegative atom and attracted to a really electronegative atom. So we have 3 different instances of hydrogen bonding between cytosine and guanine. So pretty cool. All right, hydrogen bonding and boiling point. So like I said, water can hydrogen bond, and which causes it to have an unusually high melting and boiling point. We don't think of water as being weird, but water is a really kind of weird compound. It has really high melting and boiling points for its size. It's also one of the very few molecules that expands when it turns into a solid. Water has all kinds of cool things going on. But if we look, water and HF, right, hydrofluoric acid and ammonia, all have really high melting and boiling points compared to some of these other compounds. But it's because these 3 molecules can hydrogen bond. So something like methane, right? Methane has a molar mass of 16, not 17, sorry, 16.04 or 05 grams per mole. And water is 18.02 grams per mole. Very similar molar masses. And the only thing that's different between them is that methane only has dispersion forces, and water can do hydrogen bonding. And so as you can see, methane has a very, very, very low boiling point. I don't know, it looks like it's around maybe negative 170. And water, we know, is at 100. So this is a very large difference in boiling point for a very similar molar mass. And again, the big difference here is that water can hydrogen bond and methane can't. So water and hydrofluoric acid and ammonia, right? Ammonia is 17.04 grams per mole. Again, the big difference here is that these three molecules can hydrogen bond and methane can't. All right, on to the next kind. So dipole-dipole interactions. These will be for polar molecules. Just a quick note, all of the ones that can hydrogen bond on that last slide, they are also polar molecules. They also have dipole-dipole interactions. It's just that these hydrogen bonds are a much stronger intermolecular force. Most times I will ask you, what is the dominant intermolecular force? And so you would say whatever one is the strongest. So most times, if you see hydrogen bonding, then that's going to be enough. But if I asked you to list all of the intermolecular forces, you would say, okay, it's got hydrogen bonding. It also has dipole-dipole interactions because it's polar. And it also has dispersion forces because, well, everything does. So just a quick note on that. But dipole-dipole interactions are how polar molecules interact with each other. And so reading through here, polar molecules are attracted to each other by dipole-dipole attractions when the positive end of one dipole is attracted to the negative end of another dipole. So here, right, we have this partial positive H plus and this partial negative Cl minus. And as we know, positives and negatives attract. So this attraction between the positives and negative charges here is what's called the dipole-dipole attraction or dipole-dipole interactions. So it's nothing fancy, it's just the positive end of one polar molecule is attracted to the negative end of another polar molecule. So here, right, we've got some examples. If it was a solid, right, solids have very ordered structures. And so a solid polar molecule, right, or group of them will orient themselves so that the partial positive side and the partial negative side, right, and so that they all line up and they make this nice little neat pattern. But we'll always get the partial positives being attracted to the partial negatives, and so on and so forth. It will do this in a liquid as well. Liquids are not quite as ordered, and so they'll move around a little more. But again, they will always orient themselves so that the partial positive of one molecule is attracted to the partial negative of another. Okay, and that's what we're seeing up here, the CH2O, right? It looks like this. With the red being our oxygen up there. Carbon and hydrogen do not have polar bonds, so the only dipole we would draw would be between the carbon and the oxygen. This side's our partial negative, our partial positive, right? And so our dipole is going this way. So when we look at this, the black one is the carbon, and that's our partial positive, and the red one is our oxygen, our partial negative. And so we have our partial positive carbon being attracted to our partial negative oxygen, and again, that attraction between them is what we call the dipole-dipole interaction. But again, anytime you see a polar molecule, you're going to be like, dipole-dipole forces. So here's a picture, just kind of showing you that as the dipole-dipole interactions get larger, right, we're looking for that separation of charge. We've looked a bit at these electrostatic potential maps before, right? As we get more, blue on one side and red on the other, that's kind of showing us that there's a larger and larger dipole moment. But we can also look at the blue bar. So as we are increasing our blue, right, the dipole moment going to the right, we are also seeing an increase in boiling point. So the more polar something is, the larger, the higher and higher the boiling point will be, regardless of the molar mass. Okay, so as we get to be more and more polar, we will increase the boiling point. So here's kind of a summary. So we have ion dipole, and we'll talk more about London dispersion forces in a minute. Ion dipole will be between an ion and a dipole charge. So again, anytime it says dipole, we're just talking about a polar molecule. And then we've got hydrogen bonding, okay, and then dipole-dipole interactions. And then when we get down here, these induced dipoles will make more sense after we cover London dispersion forces. But so far, out of the three that we've covered, these top three, ion dipole would be the strongest. So again, like dissolving sodium chloride in water. And then hydrogen bonding. That is a special type of dipole-dipole interaction, right? But when we have a hydrogen that's bonded to a really electronegative atom. And then dipole-dipole interactions when we have two polar molecules. And so now we're going to look at these induced dipole forces. Okay, so London dispersion forces are I would say, the hardest ones to really wrap your head around, like what it is. London dispersion forces are the temporary separation of charge that allows non-polar molecules to attract to the other non-polar molecules, right? Because otherwise, if they're not polar, then we're not having this partial positive being attracted to a partial negative. And so, how are they attracted, right? Why do they have any interactions at all? Why are they not just all gases? And so a couple things. London, so you'll hear me call them London forces, you will hear me call them dispersion forces, you will hear me call them London dispersion forces. Sometimes they're dispersion interaction forces. Anything regarding dispersion or London, this is what we're talking about, okay? London forces increase with the size of the molecule. And so most times you can look at molar mass, but I want to be really clear. It's not just because this molecule is heavy. That would be kind of a really low level answer, a low understanding answer. That would be like, well, yeah, they're correlated together, but it's not the molar mass that causes it to have a lot larger London dispersion forces. The reason that larger molecules, right, with a greater molar mass usually, have London dispersion forces or larger London dispersion forces is because there are more electrons. Okay, this is all about the electrons. And so when there are more electrons that can be polarized. And so we come up with this, polarizability. That's what you want to key into. So London dispersion forces increase with the size of the molecule because there are more electrons, which makes it more polarizable, which we'll go through. Okay, so if we look at this kind of example, so if we've got helium here. Helium, we know, is a noble gas. We know it's a gas at room temperature. It's fun. You can put it in balloons, right? Makes your voice sound funny. But helium interacts, each helium atom interacts with, other helium atoms. We could cool it down a lot and we could turn it into a liquid. So it does have intermolecular forces. So we're going to look at how atoms of helium will interact with other atoms of helium. So we know electrons, they're kind of zooming around, they're doing their own thing. Here we're going to look at electrons as particles. And so, in frame 1, they're kind of balanced. They're on, two different sides of the atom. In frame 2, they're still on two different sides of the atom. But in frame 3, both of the electrons ended up on the same side of the helium atom. And when that happens, that made this side partially negative because all of the electrons are hanging out on that side. And that made this side partially positive because there's no electrons on that side. So this is what we call an instantaneous dipole. Okay? And it just happens. They just kind of happen on accident, right? It's a happy accident. Just as the electrons are zooming around, every once in a while, more electrons will end up on one side than the other, which causes that side to be partially negative and the other side to be partially positive. Well, when that happens, when we get that partial negative on one side and the partial positive on the other, say it was near another helium atom. right? And so we had, this was our first helium atom. We had partial negative, partial positive, and it was near another helium atom. And then, so like this second helium atom sees this partial positive on this side, and the electrons rush over because electrons are attracted to partial positives, right? And so when that happens, when the electrons shift to that side, that makes this side partially negative. And this side is now left with no electrons because they all rushed over to be attracted to that partial positive. Well, when that happens, now we've got a partial positive on that side. So this atom, these electrons rush over to this side to make this side partially negative because they're attracted to that partially positive, which leaves this side partially positive, and so on and so forth, right? So this first dipole that formed, this one up here, this is called an instantaneous dipole. And these next two that formed, these were called induced dipoles. Okay, so the instantaneous dipole just kind of happens, right? Just because electrons end up on one side or the other. But when they cause a dipole to be, formed in another helium atom, then we call that an induced dipole. Okay, so we have an instantaneous dipole that causes induced dipoles. And so these attractions between these partial negatives and partial positives that aren't really normally there, right? When we have a polar molecule, we have more like permanent dipoles. These dipoles that are happening here, these instantaneous and induced dipoles, these are all temporary. These are just going to happen for like a second, and then it's going to go back to the way that it was. So these, instantaneous dipoles and these induced dipoles, these are the London dispersion forces. These are the temporary forces that are happening that cause some attraction. So they'll form and they'll go away. And they'll form and they'll go away. And they'll form and they'll go away. And on and on and on. Here's another way of looking at it. So if we look, atom A and atom B, again, let's assume that there's some noble gas. Pick whichever noble gas is your favorite, and it's that one. And so the electrons, they're just zooming around, doing their thing. And in one instant, more electrons will end up on one side of atom A than the other. And so when more electrons happen to be on one side of atom A than the other, then that side gets a partial negative charge, and this side gets a partial positive charge. And again, that's an instantaneous dipole. Just kind of happens just as we're going. And then atom B, which is nearby, the electrons see this partial positive charge, and they are attracted to the partial positive charge, which causes the shift in electrons. And so then some of the electrons, that were maybe on the right side of atom B shift to the left side of atom B and make that side partial negative, and make the other side partial positive. And again, it could, do that to atom C and D and any other atoms that happen to be nearby, right? Kind of a, chain reaction sort of thing. So this instantaneous dipole on A causes a dipole on B. It induces a dipole on atom B. And again, this is what London dispersion forces are. A dipole just kind of happens, right? An instantaneous dipole happens, and then it causes other dipoles nearby to, be induced, to be formed. Here it is in different pictures, but same kind of thing, right? Now we're just showing an increase in electron density as a darker color orange. So if, we had two nonpolar molecules, now this is, H2, and in one instant, more of the electrons end up on one side of the molecule than the other. So then, the one where there's more electrons will get the partial negative, and then this side will get the partial positive. And then that other atom of H2 sees the partial positive, and the electrons, go closer to, that side so that they hang out with the partial positive, right? It makes that side partial negative so that we can form this attraction here between the molecules. This attraction between this, partial positive and partial negative that aren't there all the time, that is the London dispersion force. Okay, so these are instantaneous dipoles that induce dipoles and then form attractions. And again, these are very weak. These are very weak attractions. So if we had, two chlorine molecules, or, two different Cl2s, right? The reason it's a little bit red in the middle is because that's where the electrons are in that bond, right? And if we say, one of them forms an instantaneous dipole, say instantaneous dipole forms on atom A. and it has, more electrons on the left than on the right, then it will induce a dipole in atom B and can form this attraction between the molecules. And it'll just happen over and over and over again until, we've got, some attractions between all the molecules. So, but again, this is not long lasting. It'll happen, it'll go away. It'll happen, it'll go away. And these are what we see as the dominant intermolecular force for nonpolar molecules. They are also happening in polar molecules, but because the dipole-dipole interactions and hydrogen bonding are so much stronger than than these dispersion forces, most times we will cite the dipole-dipole interactions and the hydrogen bonding as being the dominant force. This is really only important most times, not always, but most times in nonpolar molecules. All right, so if you hear me say this term, polarizability, right? That would be like the higher level answer. Polarizability is the distortion of the electron cloud. Because again, right, electrons don't exist in orbits, they're in clouds. And so we've talked about that a fair amount already. Polarizability increases going down a group. So on the periodic table, if we were just looking at like noble gases, we're going straight down the group of noble gases. The polarizability increases going down because there are more electrons in that atom, right? Again, like I was saying, when we look about, when we think about London dispersion forces, most time we'll, look at the molar mass because that's a really easy way to do it. But, just because it has a larger molar mass, will likely mean that it will have larger London dispersion forces, but it's because there are more electrons in the atom. So there are more electrons in the atom, so there are more electrons that are able to shift left or shift right in that molecule, okay, or in that atom. Polarizability decreases from left to right across a period. So as we go this way, polarizability decreases. This is going to be like our main one up here, polarizability increasing going up and down a group. The one left and right on the periodic table is not as common of an issue, but the reason that it would decrease going left to right is because we are getting a larger and larger effective nuclear charge. When we're getting a larger and larger effective nuclear charge, we're getting a smaller and smaller atom size, and the electrons are being held more tightly, so they're not as able to shift left and right. They're a little bit more kind of stuck in their place, and they don't have as many places to go. Again, the up and down a group is going to be more important than the left and right. Cations are less polarizable than their parent atom because they are smaller, right? We've usually removed an entire outer shell, which made our atom a lot smaller. And as we were just talking about, atoms that are smaller are less polarizable. The opposite is also true. Anions are more polarizable because they are larger. They will also have more electrons, right? And more electrons to flow around. So, looking at molar mass and boiling point. So again, like I said, they're correlated. As we increase our molar mass, we will increase our boiling point. But again, it's not just because it's heavier. So don't tell me that. I'll mark that wrong. It's because we are having more electrons, and so the atom has a greater ability to be polarized. Okay, so you'll see the trend that as you go down the noble gases and as you go down the diatomic halogens, right, we are increasing the molar mass, we are increasing the boiling point, but again, it's due to the fact that there are more electrons there and a greater ability to be polarized. Here it is kind of similarly in hydrocarbons. So hydrocarbons, right, we just have, these are organic compounds where we've just got carbon and hydrogen. So we have methane, ethane, propane, butane, right, pentane and octane. And as we go, right, these are all non-polar. Like if we think about, maybe, I don't know, propane. Propane, we've got 3 carbons connected in a chain. We've got hydrogen all around. Okay, this is a completely non-polar molecule. The only intermolecular force that it will have is London dispersion forces. And so as we increase the molecular weight, right? We can see a correlation between the increase in molecular weight and the increase in the boiling point. But again, be careful, it's not because it's heavier, it's because it has more electrons, more carbon atoms, more hydrogen atoms, and it will have more electrons to shift left and right in this molecule, which increases the London dispersion forces, which increases the boiling point. So it also has to do, these London dispersion forces also have to do with shape. So we have a couple different shapes of these hydrocarbons. So the ones we were looking at before, here, we'll back up for a second. Whoops, maybe. The one we were looking at before, these are all straight chain hydrocarbons. I know it doesn't say that, but we're assuming that these are all straight chain hydrocarbons. And what that means is that all of the carbons are just connected in a line and they've got hydrogens all around. And so when you do that, you can see this really strong correlation between molar mass and boiling point. But sometimes the hydrocarbons aren't connected in a chain. So here, this is N-pentane or neopentane, which means that they're all connected in a line. But another way that we could have made our pentane would be to connect, the 4 methyl groups to a center carbon. So these are very different. So if we look at the boiling points, right, these are different boiling points. Looking at this, the one on the left, right, N-pentane, has a higher boiling point than the one on the right, neopentane. This is because N-pentane can kind of lie on top of each other, right? All of these, if we think about, N-pentane, it could go 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5. It could, find another one, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. And it could form all of these points of attraction, right? All of this space to interact and form attractions. And then if we look at neopentane, because it's a bulky molecule, right, it's kind of shaped a little bit weird, it can't get as close to the other molecules of neopentane, and there ends up being fewer points for the dispersion forces to act, right? So we've got only this amount. So big, bulky molecules, if everything else is kind of the same, if you have a bulky molecule, it will tend to have a lower melting point and boiling point than the straight chain molecules, because the straight chain molecules can kind of lie on top of each other and have more points for these dispersion forces to act. But when you get really bulky, the molecules can't get close enough to each other or can't form a lot of points of attraction, so we tend to have lower melting and boiling points. So molecular shape matters. All right, last bit, just to kind of cover what we've done so far. It says for each pair of substances, identify the dominant intermolecular or intramolecular force in each substance. Remember, intermolecular is what we've been talking about today. Intramolecular would be the bonding forces, like ionic and covalent. Okay, and then it says select the substance with the higher boiling point. Okay, so if we look at this first one, magnesium chloride versus phosphorus trichloride. So immediately what should stand out to you is that magnesium chloride is ionic and phosphorus trichloride is covalent. So if we think about way back when, at the beginning of this lecture, I told you ionic forces are stronger than covalent forces. This should make sense to you. If you think about ionic compounds, right, like sodium chloride, right, you don't often see molten sodium chloride. It has extremely high melting and boiling points, whereas covalent bonded compounds tend to be liquids and gases at room temperature. So here, the substance with the higher boiling point, right, would be magnesium chloride. It's crazy to think about melting an ionic compound, let alone boiling it. So ionic compound here, this is an issue of ionic versus covalent bonding. Okay, and again, this would be intramolecular forces instead of intermolecular forces that we've been talking about so far. So for B is tricky. Okay, and that would be one of them that's kind of I don't know. I hesitate to say a trick question. It's a fair question, but it's a tricky one. So in first looking at this, we might think, okay, they are both polar molecules, right? Methyl bromide and methyl fluoride are both polar molecules, so they have dipole-dipole interactions. And so we would think of, okay, well, maybe let's look at which one is more polar. And if we look at which one is more polar, then we are going to say, methyl fluoride would be the more polar compound, and therefore it would have stronger intermolecular forces. However, the difference in electronegativity between fluorine and bromine is not all that big. And so their dipoles actually are fairly similar. The bigger issue here, which is like the reason I'm saying that this is a tricky question, the bigger issue here is that methyl bromide has so many more electrons than methyl fluoride. And since methyl bromide has so many more electrons than methyl fluoride, it actually ends up having a higher boiling point because of the London dispersion forces, which is crazy. We almost never see that. So I've included that example here because you're probably not going to see it many other places. So in this case, methyl bromide will actually have a larger or a higher boiling point because it has larger London dispersion forces, even though these are both polar molecules. So again, they both have dipole-dipole interactions, but because the dipole-dipole interactions are similar, because fluorine and bromine have similar electronegativities, they're going to form similar dipoles, and that actually causes the London dispersion forces to be the determining factor here. So a lot of times we'll abbreviate London dispersion forces as LDF. So the London dispersion forces actually outweigh the dipole-dipole in this one instance. Is very, very, very unusual. I wouldn't go around saying that all the time, but this is the one instance where that you would see it. And then this last one, this has, our compound on the right, compound on the left. Looking at those, hopefully you can see it really, really quick, because this OH group here, that OH group can form hydrogen bonds. The other molecule cannot form hydrogen bonds because that oxygen is bonded to two different carbons. That oxygen does not have any hydrogens attached to it. And in order to have hydrogen bonding, we need to have hydrogen attached to a really electronegative atom. We need to have hydrogen attached to fluorine, oxygen, or nitrogen. But this compound has all of the hydrogens bonded to carbons, not to the oxygen. So sometimes it may be useful to actually go through and draw out the Lewis structures. In the first one, the oxygen is attached to the hydrogen, and the other one, the oxygen is attached to two carbons. So this first one is our answer because it can form hydrogen bonds, whereas the other one will only form dipole-dipole interactions. It is a polar molecule. It'll kind of have like a bent shape, but it can't form hydrogen bonds. So just a couple things to keep in mind. Bonding forces are always stronger than non-bonding forces. So if you have an example like this first one, where you're going to have ionic versus covalent, that should be an easy one. We don't even have to think about intermolecular forces. We see one's ionic, one's covalent, done. Hydrogen bonding is a really strong type of dipole-dipole interactions. So in C, both compounds were polar, but because the first one can make hydrogen bonds, that one will have the higher melting points and higher boiling points. And then lastly, this one was, so this is about, these are a little bit out of order, but this is out A and C and B. The last one is that dispersion forces can be decisive when the difference in molar mass or a difference in molecular shape. So if we have a very large difference in molar mass, like we see between methyl bromide and methyl fluoride, then sometimes those dispersion forces can be important. They will also come into play with molecular shape. But again, do not tell me it's because of the molar mass. Make sure to tell me it's because methyl bromide has more electrons and is therefore more polarizable. And that's the end of the first part of Chapter 11, all about intermolecular forces. Get really good at these. We are going to use them for the remainder of Chapter 11 to explain lots of other properties that go along with these molecules. So as always, send me any questions you have, and I will see you next time.